Hello guys, today we're going to talk about Chapter 9, Reactions with Alkynes. So there's a couple things that alkynes can do that alkenes can't do. Right? If you remember, an alkyne is a carbon-carbon triple bond, right? So and it's sp hybridized. So all the addition reactions, or I shouldn't say all, but many of the addition reactions that alkenes can do, alkynes can do, although they're slightly different. And then there are a couple things that are specific or unique to alkynes. We're going to take a look at those too. So we'll do a little bit of nomenclature. Nomenclature. All right, we got to know how to talk about these things. In order to understand some of the things that alkynes can do that alkenes can't do, we have to take a look at acidity. Because of that, we'll be allowed to talk about the acetylide ion. That's a alkyne specific thing. And then we'll take a look at some of the addition reactions. Like hydrogenation. Halogenation. Right. Because alkynes have two pi systems, HX addition. Because they have two pi systems, they can do these things a little bit differently than the way a normal alkene can do them, which only has one pi system. We can do hydration and oxidation, which is a little bit different. Oxidation. And then last but not least, our last topic is going to be new to us. It's called tautomerization. It's kind of like a special type of isomerization. Alright, so let's start with some nomenclature, get that out of the way. It's not too difficult. It's similar to all the nomenclature schemes that we've been that we've been doing before. So nomenclature, right? So in order to name molecules, right, you need to know how to count the longest chain, you have to find all the functional groups, you have to be able to determine the priority of those functional groups, right, because some functional groups are more important, so to speak, when it comes to the actual naming than others. So up until this point, for the most part, we've just been naming alkenes and alkanes and alkyl halides, but later on, as we get more complex, we get alcohols and esters and acids and things like that. There's a lot of different functional groups that you can have, and molecules are very likely to be doubly or triply functionalized, meaning you have multiple groups. And so there has to be kind of a pecking order of the functional groups in terms of which one is the most important, which one's the least important. And so the pecking order goes like this. Acids, like carboxylic acids, followed by esters. Then aldehydes, which I'm just going to write as CHO because I don't want to write out the word aldehyde, followed by ketones. Right? So if a molecule has an aldehyde functional group, that would be named with a priority over having a ketone functional group. Then we get to the alcohols, which is going to be our next chapter, followed by amines, so those are nitrogen compounds. And then we get into the alkenes, and this is where it's a little bit contradictory, followed by alkynes. Right? Alkene chemistry is, or alkenes are rated as higher priority functional groups than alkynes, which I think is weird, but it is what it is. And then alkanes are essentially at almost the bottom of the list, but they do beat out ethers, which are just carbon-oxygen-carbon linkages. And then last but not least, they beat out the halogens, the halides, right? Like if you just have a chlorine attached, for example. Right? So as we learn more and more functional groups, if we have these functional groups both on the molecule, we want to count in such a way that the highest priority group is at the lowest number. So let's take a look at an example. If I had an alkene that looked like this, and it had an alkyne functional group, right? We have to count in such a way that the highest priority group, so the group that's highest on this list, is at the lowest number. So I could count 1, 2, 3, 4, 5, or I could count 1, 2, 3, 4, 5. Now, what we've said previously is that you should put the substituent at the lowest number, but that was the case when we only had essentially one functional group to worry about. So instead of counting 1, 2, 3, 4, 5, we should count 1, 2, 3, 4, 5. So at the 2 position we have a methyl. At the 3 position we have our alkyne, so the suffix is going to be "-ine." Drop the A, or excuse me, drop the E and add, or drop the "-ane" and add "-ine." And at the 1 position we have an "-ene," so that would be 2-methyl to represent our methyl group at the 2 position, just like we've been doing. There are 5 carbons along this chain, so pent, and if we're using the new IUPAC system, 1N, and at the 3 position we have an "-ine. So pent 1N, 3-ine. Okay. So in this case we did actually count with the alkene at the lowest, which is the highest priority at the lowest number. So that rule still applies. Let's do another example. It's a little bit different. If I had this group, or this molecule, or I had a double bond here, an alcohol here, we're going to see that this is called an enol. Oops, I lied. That's not an enol because I want a single bond there, but I want a triple bond here. Suppose I had this molecule, I could count 1, 2, 3, 4, or I could count 1, 2, 3, 4. In this case, I want to put the highest priority group, so I go to the list, alcohol, which beats alkyne, right? It's higher on the list. So this one is going to dictate which way I count. So I should count 1, 2, 3, 4, even though it puts the alkyne at position 3 rather than putting it at position 1. And so it'll be at the 3 position we have an "-ine, and at the 2 position we have our "-ol", and there's 4 carbons. So butane is our base name, right? But we have "-ine at the 3 position, so we drop the "ane" and turn it into 3-ine, because that's where our "-ine" is at. And at the 2 position we have an alcohol, so we do 2-ol. 3-ine, 2-ol. You might ask yourself, how come it's not but-2-ol, 3-ine? And I don't know if I have a great answer for you for that, but I believe it's because the OL is the highest functional group on the list, right? Alcohol is 5 versus alkyne is 8, and so it gets to be the last suffix, right? If you have multiple suffixes, multiple endings for a word, you rank them according to priority. So lowest priority, first, second, third, fourth. But don't quote me on that because I'll have to look that up. But that's what I think it is. And then the last one, do one more example. We'll do H3C, C, triple bond C, CH, O, CH3. So now we have an ether. And then what do I have? Is that an ET in my notes? I think it is. So CH2, CH3, right? So we can count 1, 2, 3, 4, 5, 6, or we could count 1, 2, 3, 4, 5, 6. Highest priority group in this case is an alkyne, because an alkyne is, where is it at? 8, whereas an ether is 10, right? So alkyne is higher priority, so we should put the alkyne at the lowest position we can. So we should count 1, 2, 3, 4, 5, 6. We treat this whole thing as a substituent, and that substituent is called a meth for methyl and oxy for the oxygen. So it's called a methoxy. So at the 4 position we have a methoxy. At the 2 position we have an "-ine, and so we say that this would be 4-methoxy hex, because there's 6 carbons in our longest chain, 2-ine. That's it. Alright, so that's it. I'm not going to ask you too much about alkynes, or alkyne nomenclature anyway, because there's much more interesting things we could do with them besides give them names. Alright, let's jump to acidity. It's important to think about acidity in carbon systems, because alkynes can do things that alkanes and alkenes can't, and so we haven't brought it up now. So if you remember, first of all, that the pKa is a measure of the acidity of a given compound, right? Lower the pKa, so the smaller the value of the pKa, the stronger the acid, right? And so, for example, HCl, inorganic acid, really strong acid, has a pKa of about -5, I think it is, right? It's a negative value, it's so small. But other compounds, like ethane, for example, we typically don't think of these as acids because the ability of the carbon to give away this proton is just essentially non-existent, right? If I rip off that proton, I generate a carbanion, an H+. They would immediately, immediately recombine to give you pK of about 50. Right? That's essentially, we don't even think of that as a as an acid. In fact, we actually will use this later on in organic chemistry too, as a base. Okay. Alkenes are slightly more acidic, but not much. So the ability to rip off that proton gives you a pKa value about 44. Again, this is a really high value, right? They're just absurdly high. We don't even think about them as potential possibilities. Alkynes, however, are a different ballgame. If I want to rip off this proton right here, it turns out I can do it because the pKa is about 25. It's still a relatively high value, but it's not absurdly high like it was for the alkenes and the alkanes. If I compare that to something that we know can be acidic, maybe it's not an acid, but it can be acidic, like an alcohol, right? And I rip off the proton off an alcohol. The pK of an alcohol is usually about 14 to 16. And in the organic world, when we say acidic, what we mean really is carboxylic acid. And that proton has a pK of about 2 to 4, so I'll just write 4, right? So this is, we would say this is an acid. We would say this can be acidic because our pKa values goes up relatively significantly. And then we say, well, this can technically, we can force it to be an acid, meaning we can use a really strong base to make this happen. But with these other two, it's not so much, right? And so that's what we're going to do when we do some acetylide chemistry. We're going to rip off this proton to make the acetylide ion, which is essentially this. And the acetylene ion, of course, is a good base because it's not such a great acid, but it also can be a nucleophile. And that's what we're going to use it for when we do, that's stupid. That's what we're going to use it for when we do nucleophilic chemistry. So let's take a look at some synthesis with the acetylide ion. Okay. First, we want to learn how to make the acetylide in the first place. So suppose I had 2,3-dibromobutane. Can you draw that structure? Should be able to. I'm going to draw it this way. H3C, C, C, CH3, Br, Br. And I'm not going to worry about stereochemistry because in this example it doesn't matter. In the presence of strong base and really hot conditions, 200 degrees C, we can have the OH minus rip off this proton, electrons snap down, and kick out the bromine to give you H, C, CH3 double bond, C, Br, CH3. And then another OH molecule will immediately come and rip off this proton and kick out the bromine to form but2-ine in this case. Okay? So we can form our alkyne like that. Another way we can form an alkyne, especially a terminal alkyne, is through a similar process where instead of starting with 2,3-dibromobutane, we can start with 1,2-dibromobutane. So we say H3C, CH2, CH, Br, CH, H, Br. And through the same process, we can use sodium amide this time instead of KOH. If you do KOH, you get the internal alkyne, and if you do sodium amide, you can actually get the terminal, meaning at the end of the chain, alkyne. And so amide is NH2 minus. It's a really good base. It'll rip off this proton. Electrons go down, bromine goes out. And another molecule of the amide would grab this proton, and the electrons would snap down, and bromine would go out. And you would get H3C, CH2, C, triple bond, C. And if you knew how to draw, the terminal alkyne. One thing I didn't mention in lecture, but I guess I'll briefly mention it here just for the purposes of, I don't know, completion or neatness. I think this is interesting. An internal alkyne can be turned into a terminal alkyne by adding sodium amide, this really strong base. That's supposed to be a 2, by the way. Right? I'm not going to show you the mechanism by how that works. It's not that complex, really. It's just deprotonate, resonance stabilize, reprotonate. But it'll convert the internal alkyne into a terminal, which is good because then you can rip this proton off using sodium amide and use it as a nucleophile. So you can go from an internal bromine all the way to a terminal alkyne, which then can be a nucleophile, just through essentially the addition of sodium amide. Alright, so once we know how to make the acetylide ion, either directly through sodium amide on a terminal dibromo species, or internally and then converting it through what's called the acetylene zipper reaction. If you want to actually look it up, you can do that. Acetylene zipper, it's kind of neat. But the important thing is that we can take our alkyne, which is terminal, and in the presence of a strong base like sodium amide, we can rip off that proton and give us the acetylide ion, and this guy will now be our nucleophile. Right, here's a great nucleophile. This is our first intro into making carbon-carbon bonds. Acetylide ions can attack alkyl halides. So if I had acetylide, and I have some type of alkyl halide like bromopropane, I can just do normal SN2 attack to give RC, triple bond C, and then 1, 2, 3. Where this is the new bond that has been made. This is the new carbon that was right there. Okay. 1, 2, 3. Oops, got one too many carbons there. Sorry about that. There we go. Okay. And I lied now. This is the bond that was made. Sorry about that. Okay, so we can do that SN2 reactions. We can also use acetylides to attack carbonyls. Right? So I can take the same acetylide, some terminal acetylide, and I can choose a carbonyl species, like a ketone, in this case acetone. Attack, electrons go up. That gives me R, C, triple bond, C, and then the original methyl groups are still there, and now I have O minus, so I get that. If I just add a little bit of water, I gotta recalibrate this thing. One of these days I swear I'll recalibrate. If I add water, I can protonate the alcohol, and I get R, C, triple bond C, methyl groups, alcohol. Okay, so that's neat. In this case it was a tertiary alcohol because I attacked a ketone. But if I didn't attack a ketone, if I attacked an aldehyde, I can get the secondary alcohol. Let's take a look. Take my acetylide again, and this time I will attack this guy, who's an aldehyde. He'll attack here, that goes up. Notice I like to draw it coming from kind of underneath, so to speak. So if you draw, like if you have a carbonyl, to me it looks like an arrow, right? It looks like an arrowhead. That looks like, let's see, how could I demonstrate this? Right, this is how I see carbonyls, right? This is where the electrons should go. Anyway, I always like to draw it like that because it's a little bit more reasonable the way it's drawn. Like if you draw it coming in like that, it's not necessarily wrong, but now you have electrons going down, electrons going up, and it's like, well, that's weird. So I like to draw it that way, but you don't necessarily have to. Anyway, this would give me the O minus, and he is still bonded to an H, or the carbon that got attacked is bonded to an H, it's bonded to an O, and it's bonded to a ring. So I would get that. That's a secondary alcohol. And then if I just add water, or you can add acid, it doesn't matter. Weak aqueous acid. You don't want to add too much because you don't want to hydrate that, and you don't want to heat it. You just want to add just a little bit of acid just to make the protonation of the alcohol step easy to do. So there you go, final product. Boom, nucleophile. Now we can make carbon-carbon bonds, right? This, up until now, in Organic Chemistry 1, we have not had a way to make carbon-carbon bonds. But now we do, so that's cool. Now we can start to modify our carbon skeletons, and we can make bigger, larger, more complex molecules. Okay, so that's the nucleophilic aspect that alkynes can do, that alkenes cannot do. And again, they can do that because they have a little bit more acidity on that terminal hydrogen than the alkene does. So let's talk about hydrogenation, our reaction type, hydrogenation. Right? We've all heard this word before because we live in America, and in all of our foods are partially hydrogenated something oil, because for whatever reason people think that's good. So if I take an alkyne, it doesn't have to be symmetrical. I can add excess H2, in the presence of some metal which acts as a catalyst, and I can turn the alkyne into the alkane. Big whoop. Not a big deal, right? It's like, yeah, alkenes can do the same thing, and in fact, for alkenes, it's the exact same reaction. Turns out, though, what happens if you didn't want to make the alkane? What if you wanted to make... this guy? Boom. What if you wanted to make the cis alkene? You wanted to stop. You didn't want to go 2 steps in reduction. You don't want to go 2 steps down. You want to go 1 step down. Turns out you can do it, but you can't use the normal hydrogenation method. Instead, you have to kind of bias the system a little bit by poisoning the metal catalyst that you're going to use. The poisoning of the metal catalyst that you're going to do is called Linlar's catalyst. Sometimes just written as Linlar. All right, Linlar's catalyst is a mixture of hydrogen, which obviously you're going to need hydrogen because you're trying to do hydrogenation. Palladium as the metal, so that's the metal surface. But if it was just this, it would go all the way to the alkane, because hydrogen and palladium, hydrogen and platinum, hydrogen and rainy nickel, all those things, they will do maximum hydrogenation. But you don't want maximum, you want partial. And so you gotta hamper his style. You gotta help him. You gotta make sure that he can't do his job. And so what you're gonna add, or what Linlar discovered you add, is some barium sulfate in the presence of this organic base, the pyridine derivative, and a little bit of methanol. All right, so you need all of this stuff. All right, it'd be a great thing to memorize for extra credit, wink wink. But if I asked you about a reaction on test, you could just write the word Linlar and I'd be okay with that. All right, so Linlar will take your your regular alkyne and give you a cis alkene. And while we're at it, if we wanted the opposite case, we wanted to take our alkyne, and we didn't want cis anymore, but suppose we wanted trans. Right, suppose we wanted to make this. How would we do that? Well, it turns out you can do that too. However, you need a different catalytic system. And in this case, you don't even use H2 and like hydrogen, gaseous hydrogen. You actually end up using ammonia in liquid state, so NH3 liquid, and sodium metal. Right? This is sodium metal, not sodium ion with a positive charge, but sodium metal with a neutral charge. Essentially, you're doing an active reduction using 1 electron transfer. And so let's take a look at the mechanism for this. The mechanism for this is that you take your alkyne, and the sodium metal says, you know what, I have this electron and I'm just sick of having an electron. It's stupid, I don't want it anymore, I'm going to give it to someone. Carbon is the only other thing that we have around. We do have a little ammonia, but he's not going to take it because he already has a full octet. And so we get a 1 electron transfer to one of the carbons, and then the electrons in the pi system move over to the other carbon. Note here that I'm using a single-headed arrow to represent 1 electron transfer and a double-headed arrow to represent both electron transfer. So what ends up happening is that this carbon ends up losing 2 electrons from the pi system, but it gains 1 electron from the sodium, and so it becomes a radical. And so that gives me a structure that looks like this. R, C, double bond, C, dot, R prime, negative charge. And you notice I've drawn the orientation here in the trans configuration or conformation, because the act of the sodium giving an electron on one side of the pi system is what pushes the electrons out the other side of the pi system. It's kind of like an SN2 reaction where the nucleophile comes in from one side and the leaving group goes out the other side. The difference is this is not a nucleophile, it's just an electron, and this is not a leaving group, it's a pi system, right? But the argument is the same. The act of coming in on one side is what makes the thing go out on the other side. Okay, once we form the carbanion, which is a negative charge, it will immediately get protonated by some ammonia that is in solution. And we intentionally use liquid ammonia because liquid ammonia is hella cold, and so it kind of controls this reaction, because obviously having a radical next to a negative charged ion is probably not terribly stable. And so We want to really make this reaction cold so that we don't have to worry about weird, crazy radical reactions, polymerizations, and otherwise other things happening, right? So that gives us something like this, our carbon radical. Another atom of sodium will say, I also don't want my electron. I heard you're taking electrons. So the carbon says, yeah, I'll take your electron. I'm okay with that. That gives us our anion. And then there's just a subsequent protonation step. Will take us to our trans product. Okay? So it's not actually too bad of a mechanism, but it's definitely unique, right? I don't think I know of any other mechanisms in organic chemistry where you do two one-electron transfer steps generating carbanions in the process, right? It's just a very unique mechanism, right? So it would be the the formation of a transalkene from an alkyne using sodium and ammonia. Okay, and so a simple question that you might see on a quiz or an exam or something like that would be, I try to keep the geometries reasonable, right? What goes in the box, right? You need to identify that this takes an alkyne and gives you the transalkene, and so your product should necessarily be 1, 2, 3, 4, 5, 6 carbons long. 1, 2, 3, 4, 5, 6, and the double bond will be between carbons 1, 2, and 3, 2 and 3. So there, trans. Technically, you would also get 2 molecules of NaNH2. We've seen that before. That's sodium amide, and that gets generated in a couple places. One of the NAs gets generated here, one of the NAs gets generated here, one of the NH2s gets generated here, the other NH2 gets generated over here, right? So that's the side product. I mean, you can collect that and use it as a base to do other stuff if you want, but I'm not as interested in that, honestly. So, okay, so that is our hydrogenation reactions for the alkynes. That's all I'm going to say about that. I'm not going to give you lots of examples. Let's move on to halogenation. Halogenation, all the Asians. Halogenation of an alkyne. So you take some alkyne, like our favorite butyne. Everyone loves to say butyne. And we're going to add excess bromine in the presence of a non-nucleophilic solvent or a non-protic solvent, like dichloromethane. And like I said, excess. And in the presence of excess, we get 2233 tetrabromobutane. You should know how to go from the language, the word I just said, to the structure. Butane would be this, 4 carbons long. I don't know what happened there. CH3. I don't know why sometimes it works and sometimes it doesn't. Killing me, smalls. And we put bromines across the triple bond. Okay. Unfortunately, under this structure, you cannot stop at the transalkene or or even the cis alkene. It goes all the way to the alkane because this is excess, so you have no way to control the reaction. All right. So how does this mechanism work? It works the same as the halogenation bromine addition for an alkene. The triple bond attacks the molecule of bromine, forming a induced dipole effect. So we're drawing the mechanism here, right? The bromine then will kind of bridge the gap and say, all right, I will bond to both carbons, forming the bromonium ion, right? Bromine with positive charge, 3-membered ring. The bromide that just got kicked out will then come back from the other side and attack. It will attack the most accessible carbon. In this case, it's symmetrical, so it doesn't matter. I think it's most accessible. I should probably look that up. But in this case, it doesn't matter, so bromine attacks to give us H3C, C. Well, I'll actually swing this down. Br, H3C, double bond C, Br, CH3, right? And then this molecule immediately attacks another molecule of the bromine to repeat the mechanism to give you the bromonium ion again. Which then gets attacked by another bromide, specifically the bromide that was just created. And it doesn't matter if you tack this one or this one again, because it's symmetrical. And that takes you to your product. Right? So it's the same mechanism, right? You're just doing it twice because you have one extra pi system to play with. Now, in this case, we were adding bromine Br2. So we had a bromine here and a bromine there. Then we had a bromine here and bromine there. It's a little bit different when you do HX addition, because now bromine is not the same, or X is not the same as H. Right? So HX is like HCl, HBr, HI. HX addition. It's a little bit different. Let's take a look at that. Take an alkyne, perhaps a terminal alkyne to make this one a little bit easier, and we do two equivalents of HX. What we get then is the geminal dihalide, like this, and we don't get the vicinal dihalide, meaning both of the halogens are on the same carbon, geminal. They are not on adjacent carbons, vicinal. So you don't get X here and X here, you get both of them here. Why is that? Hopefully you should know why this is by the time you get to this point in the class. But if you don't, let's draw the mechanism so that it makes sense to us. So if we have HX, triple bond attacks, go there. Markovnikov's rule says what? It says the H goes to the location that has the most H's, or it says the positive charge goes to the most stable carbon, or the carbon that will have the most stable positive charge, however you want to look at it. And so the double bond go here, and then the carbon that has one hydrogen will gain a hydrogen, which means our positive charge ends up here. So when X minus attacks, it will attack there, and you get this. C, X, double bond C, H, and H. This molecule will immediately attack another molecule of HX. When it does, you get the same argument. You get C, 8. The Markovnikov's rule says the positive charge goes to the most stable location, which again would be a secondary versus a primary, so that argument's true. But in this case, because there's already an X attached, a halogen, the halogen can actually help out that carbocation, and I'm running out of space here. Through this resonance contributor. Right? It can push his electrons in and put the positive charge and double bond to that halogen, chlorine, bromine, or iodine. I don't think fluorine can do it, and if it does do it, it's not very well. So essentially we're talking about HCl, HBr, and HI. Then when X minus attacks, because it was generated right here, oops, let me put the X minus right here. X minus will attack the positive charge and will necessarily lead you to the geminal dihalide rather than the vicinal dihalide. Okay. Let's see. We can do, so that gives us the Markovnikov addition, the geminal dihalide. But just like before, when we had Markovnikov addition of HBr and anti-Markovnikov addition of HBr, we can do the same game with alkynes. So if I take this, and I'm just going to write PR for propyl because I'm lazy. I can do an anti-Markovnikov, and remember with anti-Markovnikov it has to be HBr in the presence of peroxide, and that will take me to the alkene, which in this case will look like that, and you'll get E and Z. I'm not going to draw this mechanism for you. I would like you guys to do it. If you don't remember how to do it, go back and look at your HBr anti-Markovnikov addition notes from chapter 8. It's the exact same mechanism, right? So I'll give you a hint. The first step is homolytic bond cleavage between the oxygens in the peroxide. All right, so you guys can go look that up and try and write it out on your own. I will save that as an exercise for you. All right, next is hydration, right? We already know about hydration of alkenes, right? So hydration of alkynes is a little bit different, okay? So if I take an alkyne, and normally, if it was just an alkene, I would just add acid water H3O+, and I'd be done with it. Or if I wanted to make a non-rearrangeable alcohol, I could use mercuric acetate and do oxymercuration. Here, however, we have to change the game a little bit. Instead of doing oxymercuration, we're going to do the alkyne version of that, which is mercuric sulfate. Mercuric sulfate plus an alkyne will give us this weird structure, well, it's weird to us, where the alcohol is directly bonded to the alkene. This structure is called an enol. Why is it called an enol? En, because it has a double bond, like an alkene. Ol, because it has an OH, like an alcohol. And we chemists are very smart, so we smash those things together and say enol. Right? Enols do a process called tautomerization, which we're going to learn next. For now, just trust me. And they turn themselves, or this enol, anyway, will turn itself into a ketone. And we call this the keto form, because technically this is an equilibrium. Alright, so how the heck does this work? I don't understand this, Jay. I think you're lying to me. Haha, I will prove it with a mechanism. Alright, so the first thing that happens is mercuric sulfate exists essentially as mercury 2+, right? So the triple bond, which has negative charge, or I shouldn't say negative charge, triple bond which has electrons in its pi system will be attracted to the positive charge, and you will get R, C, double bond, C, H, Hg, 1+, so essentially a reduction step, and a positive charge here. Okay, water, of which there will be lots of that stuff, will attack our positive charge to give us R, C, O, H, O, plus double bond, C, mercury hanging out. Right? Does this look like anything we've seen before? This is what we get when water attacks in the oxymercuration-demercuration reaction with an alkene shortly after the mercurinium ion has been destroyed. And so it's essentially the same structure. Okay, so we just deprotonate there to give us that. And then that gives us R, C, I'll draw it again, OH. So here's our enol essentially. But we got mercury hanging out. Okay. Now the double bond, oh man, come on, you stupid. Double bond will now attack a molecule of acid, whether H2SO4 or H3O+, doesn't matter. I'm just going to draw H3O+ because it's quicker to draw. Giving you R, C, O, H. When we break the double bond, the proton goes to the carbon that has more protons, right? The normal Markovnikov rule. So this carbon, which had one hydrogen, will gain a hydrogen, and the mercury here, still mercury plus, and this carbon has a positive charge. This guy is part of a resonance set because electrons from the oxygen will say, hey dude, carbon, you're missing some electrons, dude, let me help you out. Carbon's like, thanks bro, you're my bro. I think carbons are really friendly. If I was microscopic, I could take the magic school bus. I would check and see if they're friendly. Okay, and then the last step is just to kick off the mercury. So if mercury leaves here, come on arrow, killing me Smalls. Then we get R, C, double bond, C, H, H. Mercury goes back to being 2+ because it lost 2 electrons, or 1 electron in the bond, and the enol is still hanging out. So this then is our enol, which then tautomerizes. Right, so it's a slightly different mechanism, right? We don't ever make the mercurinium in the way that we do with the oxymercuration reaction, but we do mercurate the molecule, and then mercury comes off, and we still do a mercury 2 to mercury 1 reduction, where when we did oxymercuration, we essentially only used mercury 1, and we went from mercury 1 to mercury 0. So it's analogous, but not exactly the same, right? So if we just do a summary reaction then, an alkyne, like 1-butyne, and we add mercuric sulfate in the presence of H2SO4 again, and of course we need a little water. What will we end up? The carbon that is not terminal, right? This is where the OH group will go because this is the Markovnikov addition location. Will be the one that gets the oxygen. And so we'll get this molecule, which we don't know how to name yet, but it's called 2-butanone. Okay. So make sure you can draw this mechanism out that I just gave you for this reaction, because that would be a good test question, I think. All right. So that's the Markovnikov addition to hydrate the alkyne. But what if we wanted to do the anti-Markovnikov addition? Just like with the alkene, we could do, let me try it again, hydroboration, oxidation. But again, we're doing it with an alkyne, not with an alkene, and so we have to use reagents that are a little bit more specific to an alkyne rather than to an alkene. Right? So if we take an alkyne, we'll use a terminal one in this case. Now we're going to use SiA2BH, isoamyl borane. Isoamyl, okay, so a little bit of a history lesson here. SiA is the stupid way to write what I think should be called, is the stupid way to write isoamyl. Iso meaning has a tail or has like a terminal dimethyl group. Amyl meaning the old-timey word for pentyl. So this is essentially an isopentyl group. Okay, let me get the exact structure for you. So the structure of SiA is H3C, C, H3C, that's the iso part, CH, CH, that should be just regular CH here, bonded to whatever the molecule is, and CH3. Right, 5 carbons. This is called isoamyl. In modern terms, it would be called isopentyl, but in the old-timey word, it's just isoamyl is what it was used, so it's kind of just grandfathered in. So SiA stands for isoamyl, and it looks like that. The important thing to note is that it's a volumetrically large group. That's what we care about. It's big and fat, it gets in the way, it sterically hinders the chemistry. So if we take isoamyl borane, so where we attach 2 of these things to a boron, what we'll end up doing is boronating the molecule, just like we did when we did hydroboration oxidation of an alkene. And we get boron and its 2 isoamyl groups hanging out. We can stop there and isolate that if we want, but the oxidation step where we add peroxide, and I ran out of space, I'm going to leave that up. Right, the oxidation step will knock that off and turn it to an alcohol, and so our final group, or our final product then, would be this. Right, so this turns into that through the presence of peroxide and a little bit of base. And this mechanism, where we turn this group into this group, we do not have to know, but you can look it up if you want to. It's nice, long, and complex and annoying, so don't worry about that. But what you are wondering, I'm sure, is, well, how do you go from this to that? It's very, very similar to the hydroboration oxidation of an alkene, but now we have a big old fat borane rather than using BH3 and THF. So let's draw it out, and we'll talk about why it makes sense. Hydrogen, boron, and I'm just going to write SiA for isoamyl. And you know what maybe I'm going to do, just to, that's interesting, my eraser function disappeared. Oops, and my pen is dead. Alright, pause the video, be right back. Alright, sorry about that, I'm back. Instead of drawing SiA like that, I'm going to be a little silly with it. I'm going to draw it really stupidly big. Right, I'm trying to keep the bond lengths about reasonable. But I'm just going to draw it real big to represent the physical size of this space. Right? The whole point of using an isoamyl group is that it's big, it's bulky, it gets in the way. Right? And so when I add this isoamyl borane to my alkyne, we get this electrocyclization type reaction, because remember the boron has an empty p orbital. It gives me a structure that looks like this. R, C, double bond C, H, right? And I'm forming a bond to the hydrogen, I'm breaking a bond to the boron, I'm forming a bond to the boron, and I'm breaking the pi bond. And then the isoamyl groups are out here. So this is my transition state. Okay? Because these big SiA isoamyl groups are here, it prevents this from happening again. Right? Since you have a pi system and you have a boron that has an empty pi orbital, or a p orbital, excuse me, you would think, at least on paper, that you could do what I've drawn right here. But because of the physical size of these isoamyl groups, right, they take up a lot of volume, they physically prevent another boron molecule from coming in and doing what I just drew. And so you only get one addition of the boron to the alkyne rather than two. And so you necessarily end up with this rather than the diadduct. Right? So that's really the important thing to note here, is that these groups too big to allow double addition. They physically get in the way. And so it doesn't have to be isoamyl groups, right? If we go up here and we look at the isoamyl structure, right, it doesn't have to be that. It could be a boron that's bonded to some magic structure that I just made up right now. Right? It just needs to be something that's big and fat and gets in the way. It does have to have a hydrogen, of course, because this bond needs to go to the alkyne, and the alkyne needs to go there. So you do have to have the open orbital, and you do have to have the hydrogen, but the rest that's attached, it could be anything. And if you want to make them aromatic, by all means go ahead. If you want to tack on some hydroxy groups, once you start adding functional groups, then it gets questionable, but there's nothing stopping you, right? If you change them from hydroxys to methyl ethers, right? Doesn't matter. It just has to be something that physically gets in the way. And so if you were doing this reaction in a lab, or a real reaction, you might have to intentionally tinker with what's attached to get the best yields and things like that. Okay? But the important part to remember is that you need a big fat group that prevents double addition. That's the key. Then once we have that, we just oxidize it off with peroxide and base, and again, you don't have to know this mechanism, and that gives you the enol. Enol, which tautomerizes, T in a bracket. In this case, when it tautomerizes, it will tautomerize to the oxygen on the terminal carbon, which in this case will give you the aldehyde. So now we have a way to make ketones and make aldehydes through tautomerization of the enol, which comes about through alcohol addition of either hydroboration oxidation or hydration of an alkyne using mercuric sulfate. All right. Last topic in chapter 9, tautomerization. So how does this last magic step work? I asked you to trust me, but now I'll prove it to you. T-A-T-O-merization. All right. When I get large complex words, I like to spell them out with like a pronunciation key. So you pronounce tautomerization, or at least I pronounce it as I. This supposed to be an I. Zation. I guess if I'm really doing it, it would be zay, shun, like that. Tautomerization. Okay? Each one of these structures is called a tautomer. So if I take the enol tautomer, looks like this, en and enol. Let's use a simple generic one. This is called a tautomer, like an isomer, but it's a specific type of an isomer. I can do acid catalyzed, or I can do base catalyzed tautomerization, right? So I can do it under acid conditions, or I could do it under basic conditions. Let's take a look at the acid conditions first. In the presence of acid, we have a double bond. What do double bonds do in the presence of acid? They get protonated. And so the same thing happens. Double bond gets protonated, and the positive charge goes to the most stable location for a positive charge. That's Markovnikov's rule. Or we could say that the hydrogen goes to the carbon that has the most hydrogens, which means it would go to this carbon. And this guy is part of a resonance contributor, where oxygen helps out because he's a bro. It says, there you go, helping you out, dude. To give you that, that's our resonance set. And as you can see now, all you need to do is take some of the water from the earlier step and deprotonate, and it takes you to your keto tautomer from your enol tautomer. So it's protonate, resonance stabilize, deprotonate. That's our generic structure. If we do base catalyzed, right, it's similar. What do bases do? Bases deprotonate things. So I start with the same enol, but in base conditions, we have something like hydroxide or something that can remove a proton. The base gets deprotonated. That gives us a structure that looks like this. O minus, double bond C, H, and H, which is a resonance contributor of this guy. Now I'm pushing electrons down. C. And then this grabs a proton from water, not from acid, but from water, because there's no acid around, because we're basic conditions. And that takes you to the exact same product, that. And you still regenerate the OH minus. Right? Just like here, you regenerate H3O plus. So you get the same product. It doesn't matter if you do acid catalyzed or base catalyzed. But what matters is that you have two ways, acidic conditions or basic conditions, to turn an enol into a keto tautomer. And just like before, if we had a terminal alkyne, so if we did something like, we'll use our but2-ine again because everyone loves that. Oops. Let's say we did but2-ine, and we do NH2. This is our, whatchamacallit, acetylene zipper reaction. CH3, CH2, C, triple bond C, H, right, to give us the terminal alkyne. Then we take that and we do hydroboration oxidation, so BSIA2H, followed by peroxide, H2O2. That would give us CH3, CH2, CH, double bond C. It would give us the enol that looks like this, ENZ. And the enol will tautomerize under either acidic or basic conditions, it doesn't matter. Oops, don't forget my OH minus here. To give us this. The aldehyde. Why do we get the aldehyde? Meaning the oxygen is on the terminal, the fourth carbon, or first, because we should count right to left, right? Because the alcohol of the enol was on the end carbon. How did we get it on the end carbon? Well, we did hydroboration oxidation of an alkyne, in this case, of a terminal alkyne. Whereas in the previous example, our oxygen ended up on the second to last carbon, which is a ketone rather than an aldehyde, and that's because the enol could have came about from just a normal mercuric sulfate and aqueous acid. Right? That's the reaction I showed earlier. So depending upon where you want the final oxygen to end up on the molecule, do you want it to be terminal at the very end, or do you want it on one carbon over, you have to choose the right addition reaction. Hydroboration oxidation, like this, or mercuric sulfate. All right, that is the end of Chapter 9, and I will be doing Chapter 10 soon. Have a good weekend, guys.